Hello, this is number 9 on the practice final. We're given a second order differential equation that describes a continuous time LTI system. And we want to determine the transfer function h of s and the impulse response h of t. So asks us to find h of s. So we're given second order differential equations. We know the properties of the Laplace transform is that we can solve this algebraically, and the differential operator is just going to give us s times the transform of y and s squared times the transfer of y respectively for these. So we get s squared y s minus 2s ys minus 3ys equals xs. The transfer function h of s is y of s divided by x of s. So we're factoring out the y of s from each term and then dividing through by x of s and dividing through by these, and we get 1 s squared minus 2s minus 3. Here comes the fun algebra. Hopefully you guys are all still proficient in factoring. It doesn't matter what way you do this, whatever way you find convenient. This one's pretty easy to factor. We can rewrite this. So in case you forgot, we want to find two numbers that equal negative 2s when we add them and equal minus 3 when we multiply them. So minus 3s plus 1s minus 3 now factor out an s from these two terms, factor out a 1 from these. Now we have a common factor. We can rewrite this. Factor out the s minus 3 gives us s plus 1. So that's the transfer function, and that's A. It asks us to find the pole 0 plot, which is actually just asking you to find where the discontinuities are in the domain of the transfer function and or where it's not defined. So the poles for this function are where the poles of a function are the zeros of the denominator. So the zeros for this function, you would say s minus 3 equals 0 gives you the pole of s equals 3, s plus 1 equals 0 gives you a pole of s minus 1, that's 3. That's minus 1, so these are places where the function is not defined, or rather undefined, sorry. And there are no zeros for this function because the numerator is just 1. So that's A. B asks us to find h of t if the system is causal. So the condition for causality is that the region of convergence for the transfer function is the right half plane RHP to the right of the rightmost pole. So that looks like this. Here's our pole at -1, our pole at 3. So this is a dashed line because our region of convergence does not include the point at 3. So let's rewrite our transfer function. It's h of s equals 1 over s plus 1 times s minus 3. We're trying to find the inverse Laplace transform, so we need to get this into something that we can look up on the table of transforms we've been given. So we're going to do partial fractions. You can do this however you want. This is the way I do it. You might find some other way easier, so you should know how to do this though. And if you don't, go read up on it. There's a lot of resources, Khan Academy, Paul's notes, etc. Okay, so I'm going to bring this denominator over to here, and we can write 1 is equal to a. These factors will cancel right here. We get a s minus 3 plus b. These factors will cancel, so we get b s plus 1. If s equals 3, then we're just plugging back into this function right here. So if s equals 3, s minus 3 is 0, so the a cancels. We get b, s plus 1 equals 1, so b times 3 plus 1 is 4, b equals 1/4. Same deal, if we let s equal -1, then this cancels right here. Then we get a times -4 is equal to 1, so we get a equals -1/4. Let's go ahead and rewrite this now. H of s equals -1/4 s plus 1 plus 1/4 s minus 3. Now we're in the right half of the plane to the right of the rightmost pole, the rightmost pole being 3. So we know that s is greater than -1 and s is greater than 3. And when you combine these conditions, you get the region of convergence for h of s, which is s greater than 3, because we're in the right half of the plane to the right of the rightmost pole 3. So we go to our table of transforms. you need to be careful that you're picking out the right transform for your condition. I wrote s greater than -1 and s greater than 3, but really I should have wrote the real part. Because that's how you'll see it on the table of transforms, because s is possibly a complex number. So the transform of interest is 1 s plus alpha transforms to e minus alpha t ut, and the condition is that the real part of s is greater than minus alpha. So for this first one, right here, alpha is 1. So we see that this transform here pretty much matches exactly, so we can just go ahead and write h of t equals -1/4, because we are greater than -1. So in our region of convergence, that is, so we get e minus t ut plus 1/4, and alpha here is going to be alpha here would be -3, and the real part of s, we take it over here, we would have real part of s is greater than -3, so the real part of s is greater than +3. That's true. Our region of convergence is for all values with the real part of s greater than 3. That's the right half plane to the right of the rightmost 0. So we get 1/4 e. Alpha here is -3, so -3 is +3 t ut. Okay, so that's part B. So now part C is asking us to determine h of t if the system is stable. If the system is stable, we know that it has to include the j omega axis, otherwise known as the imaginary axis. So a region of convergence would be this. So we have h of s, we know it's so we want the real part of s to be less than 3. That goes there, that's the condition on that. And we want the real part of s to be greater than -1. So we go to our table of transforms. Again, make sure you're getting the correct one. For this first term here, it's going to be minus e minus alpha t u minus t maps to 1/s plus alpha, and the condition is that the real part of s, excuse my curly brackets, they're kind of hard to do on this tablet. My brackets usually look a little better than that, but here's our condition. So we see the first part of this one's gonna go h of t equals 1/4. This matches to here. In this case, alpha is -3, so if you put -3 in here, you would get real part of s is less than 3, so we get 1/4 times minus e. Alpha is -3 plus 3, because they cancel out. T u minus t. Now the second term is just the previous transform that we used, which is, let's go look at our table. E minus alpha t ut goes to 1/s plus alpha, condition with real part of s. Greater than minus alpha, so alpha is 1. If we put that in here, we'd get real part of s greater than -1. That meets our condition here and here, so we get plus 1/4 e minus t, because alpha is 1 ut. Okay, that's that is, sorry, I missed a negative sign right here. That was -1/4, so when we bring this down, it will be -1/4 here as well. Okay, now part D is asking us to find h of t if the system is neither stable nor causal. So then the ROC is the left half of the plane to the leftmost pole, so that is going to look like this. Remember, -1 is not included because it's a pole. So again, we rewrite h of s is equal to 1/4 s minus 3 plus -1/4 s plus 1. Okay, so the condition is that on this one is that the real part of s is less than 3. The condition on this is the real part of s is less than -1. These two conditions together give us the region of convergence. So again, this is going to be a situation where we go to our table of Laplace transforms. In this case, we're going to be using this condition right here for both of them. So let's rewrite that down here. E minus alpha t u minus t maps to okay, so we can write h of t now. H of t equals 1/4. For this first one right here, our alpha is -3, so if we put -3 in here, we get real part of s is less than minus minus 3, that's plus 3, that's our condition, so we get, forgot that negative sign right there, we get minus e minus 3 plus 3 t u minus t, and then we get minus 1/4. We go here, the real part of s is less than minus 1. In this case, alpha is 1, so we go here, real part of s is less than minus 1. That's good, the condition is met. So we get minus e, alpha is 1, minus t, u minus t. There we go. That's the final answer for D. This was number 9 on the practice final. I'll see you in the next video.